Planetarium today for our talk. We're kind of we're providing the hosting, and then it's actually we've got National Park Service and we've got LVAS and everybody involved with this, and it's always good to have partnerships that work so well with this. And so I'm going to turn things over to Ashley Pipkin, and she's going to introduce our speaker for us.
Yeah. So. Yep, my name is Ashley Pipkin. I work for the National Park Service in the Natural Sounds and Night Skies Division. Myself and my colleagues in the Night Skies Division work in partnership with Parks, and we work in partnership with the Las Vegas Astronomical Society, CSN Planetarium, and many others to increase scientific understanding and inspire public appreciation for the value and character of the undiminished view of the cosmos. We're so thankful to have Dr. Buie here today, and before introductions, I want to thank CSN again and thank the Las Vegas Astronomical Society. Without further ado, I would like to introduce our speaker, Dr. Buie. Dr. Buie is a planetary scientist and observational astronomer at the Southwest Research Institute in Boulder, Colorado. He earned his PhD from the University of Arizona in planetary science. Dr. Buie serves on the science team for NASA's New Horizons and Lucy missions. His work centers around exploration of the outer solar systems with telescopes, big and small, on the ground and in space. Today he's going to be discussing research from the New Horizons mission and the first ever flyby of a cold classical Kuiper belt object. Ladies and gentlemen, Dr. Buie.
Well, thank you very much for being here and sharing part of your Sunday afternoon with me. And I will try to share with you some of the things that I've been working on for a fairly long time. But I don't do it alone. And I want to share with you basically a story that contains perseverance, that's working and not giving up, collaborations, working with lots of people to get something done that one person can't do alone. And above all else, it's all about telescopes. I may not talk specifically about them, but every single piece of this story involves one kind of telescope or another. And those are magical instruments for me. And my life has been intertwined with them ever since I got to see my first one. But let me launch right into this and show you some of the collaborators I've been working with the story that I'm going to tell here, which spans about, well, I don't know, maybe about 80 years. Not all of it in my lifetime, but some of the names I'm going to show you here are on the top paragraph there. These are all of my cohorts on the New Horizons mission that built and launched the spacecraft across the solar system and working on from ground-based support to try to make this mission a success. And we've also got in the bottom paragraph a lot of the facilities that I've used over the years, from the Subaru Observatory built by the Japanese on Mauna Kea in Hawaii, Magellan Observatory in Chile, and Sophia, an airborne observatory, so that's a big telescope built into an actual airplane, and lots of other people that have helped along the way. But wait, there's more. This isn't all. I ran a couple of occultation expeditions. I'll explain what that is in a second, but that includes a lot of people. And in 2017, here is all the people that helped me, both in South America, mostly in Argentina, and also in South Africa, and people from both countries, but also lots of people from the United States that I know and work with to chase these occultations. And in 2018, a whole nother crew, because here we went to Colombia, we went to Senegal, and some of the people that worked with me in 2017 came back again. Some people were busy, and I brought other recruits in. One thing that I would point out here in this slide to show you just how internationally connected we are in this work, in this project, is the European and Northern Africa habit is to use uppercase for the surname, so the last name is all uppercase, so you can immediately scan through this list of names and you can just get a sense for how many people that were involved that were actually in Senegal or Colombia at the not just those coming from the U.S. And there's one particular name here that I would point out here. See this name, Mackie Saul? So, pink cookie for anybody that can tell me who Mackie Saul is. Any ideas? He's actually the president of Senegal.
What?
I've never had a head of state as a collaborator on a project before, so that was a new experience for me, and I'll show you some aspects of that work. But it truly does take a lot of people to build up a team to do this work. The timeline of exploration that I'm talking about here begins with, in 1930, Clyde Tombaugh, who was hired by Lowell Observatory to search for a planet beyond Neptune. And shortly after he was hired, he indeed found it. And you all know this is Pluto. It was discovered back in 1930. And we didn't know it at the time, but that was actually the first Kuiper belt object to be discovered. These are objects that live out beyond Neptune in the outer reaches of the solar system. In the 1950s, we had the beginning of space exploration, starting off with manned missions primarily, but that transitioned into unmanned spacecraft afterwards. And in the 1980s, I come on the scene, and I began with an intense interest in studying Pluto in graduate school at the University of Arizona. At the time, Pluto was doing a dance with its moon that meant it would called mutual events, where the moon would pass in front and block part of what you see for Pluto. And 3.5 days later, this moon would go behind. And it was a tremendous opportunity to learn more about Pluto. And that really launched my career working on that particular aspect of Pluto. And I recognized then that there was a chance in my lifetime, in my career, we could send a spacecraft to Pluto. Now, I don't know how to do that, but I do know that you have to understand a lot about an object and get other people excited and interested in a place in order to spend a very large amounts of money to build a spacecraft and buy a rocket and send it across the solar system. Along with that development, in 1990, we launched the Hubble Space Telescope. I was actually working in Baltimore for the Space Telescope Science Institute, the organization that runs and operates the Hubble Space Telescope at the time of launch. And Hubble, it has a very special place for me. It's one of my favorite telescopes, and it's been part of my career from the beginning, both as I was starting out, after graduating, but also for exploring the solar system. And I did a lot of work on understanding Pluto with that. And Hubble has a story to play, or a part to play in the story of MU-69, the target for New Horizons that I'm going to get to in a minute. So, not just a year after Hubble is launched, we find the second Kuiper belt object. And people call it, that's when the Kuiper belt was discovered. Before that, we just knew there was Pluto there. But now we've got another object out in the outer solar system. Everybody was pretty suspicious by that point that there were a lot of things out there we hadn't seen yet. And now we've got proof. And from that first measurement, knowing what it took to find it and how much sky you had to cover, and making some estimates, everybody instantly realized there's thousands upon thousands of these objects out there to be discovered. And I got very heavily involved with studying that and was part of a survey team and discovered more than 1,000 of these Kuiper belt objects in the late 90s and early 2000s. Those two things together, Pluto, what I was doing in graduate school and then shortly thereafter with the mutual events, and it was a resurgence in interest in Pluto, and then the discovery of the Kuiper belt really led to a community appreciation. We've got a whole nother zone of the solar system that just has not been explored yet. We're now calling it the third zone. The first zone being terrestrial planets, Mercury, Venus, Earth, Mars, and we've got the giant planets from Jupiter out to Neptune, and the third zone is the Kuiper belt. It's this region out beyond Neptune. It's cold and dark area. And those two things together gave us the support and the interest to get funding for a mission to send a spacecraft there. And there's many proposals and many competition over who's going to get to build and fly this spacecraft across the solar system. In 2001, which is a very auspicious year for if you're into science fiction, in fact, we had a meeting for the Division for Planetary Sciences. We have a meeting every year in different places. I was one of the co-hosts to host that meeting in New Orleans. And because I'm actually originally from Baton Rouge, Louisiana, so the locals there sort of, I wanted to host the meeting and get everybody coming down to Louisiana. In the lobby of the hotel, we had the convention, we had the monolith from 2001: A Space Odyssey, the black object. It was very funny. We just set it out there in the middle of the lobby. No signs, no anything, it's just there. And we didn't tell people we were going to have it. And it's the same size and proportions as they describe in the book. So I forget exactly what it is. There's a magic ratio in there, but it's just sitting there. And I every time I walk by, I look and somebody's over there walking up to it. Just like from the movie, you know. I thought that was pretty cool. But you know there's just this thread of exploration and exciting the psyche of us as people. If we like to explore, everybody is kind of interested and has some innate curiosity, certainly born with it. Some people leave it aside as they get older, but all of us are born to explore and figure out what's going on in the universe. Okay, so New Horizons is selected for flight. We knew we were going to go to Pluto. We were designing the spacecraft to do that. And beyond Pluto, we know we want to go to a Kuiper belt. But, as luck would have it, or otherwise, we didn't actually know of an object that we could get to. And the reason for that is it's a region of sky that no one in their right mind would ever look for an object because it's too complicated. I'll show you an example of why that's such a crazy thing to do in just a second. But we knew we had to find an object if we were going to see anything after Pluto. And in 2004, we figured, okay, it's time to kind of start working. We haven't launched yet, but let's get going. Let's take some data. Maybe we'll get lucky and we'll find something. 2006, we were launched. We haven't found an object yet. Time goes on. We're flying across the solar system. We got plenty of time. We got lots of time before we get to Pluto. 2011 comes along, and we're still not finding anything. Let's do more. Let's get bigger telescopes, more people involved, and work harder at this. We increase our efforts. And then along comes this mission called Gaia, which plays a very crucial role in this story. And I'll get back to this, but basically it's a mission that measures the position of all the stars in our galaxy. And not only the position, but how fast they're moving, so that we know exactly where they are. And I'll tell you why that's important here in a minute. Again, here we go, a couple more years have gone by, and we haven't found anything. 2014 comes along, and we either have to find something this year, or it's game over. And at that point, we've used every resource that exists on planet Earth, on terra firma, and still haven't found anything. It's like, well, what else is there? Well, okay, Hubble Space Telescope's up there. We haven't tried that yet. And it's actually kind of a crazy idea because it takes a lot of data and a lot of time on the Hubble to do this, but it's our only option. We came up with a plan, and we did this survey to look for objects. Thankfully, we found something, and I'll show you a little bit more of the details about that, but we found something just in the nick of time. We flew by Pluto in July 2015. Then in August, we selected the target that we were going to fly to. We picked it out from what we found in the survey. And then in October 2015, we did the trajectory correction. That means we turn on our rocket engines and push the spacecraft in the right direction so that we go to the object that we had just found. If we didn't have an object discovered in 2014, then in 2015 in October, we wouldn't have known what to do, and then we would have run out of time and we would not have had anything to go to. 2017, we finally, Gaia launched in 2013, we needed the star catalog. We finally got it in May of 2017. If that had been 1 year later, I'm not sure we would have succeeded flying by the object that we knew existed. So we needed that for navigating the spacecraft up to this tiny little object in the outer solar system. Then we had June 3rd, the first occultation team. This is a very big part of the story because occultations give us data that we can't get in any other way. So some of you may know what occultations are, some of you may not. I'll explain it very briefly. Occultations are when something gets in front of something else. So if I'm standing here and you're looking at me, there's part of the dome behind me you can't see. So you could say that I'm occulting part of the dome. In the case of a scientific experiment that we're trying to do, what happens is there's a star way out there in the galaxy somewhere, and an asteroid or a planet or a Kuiper belt object passes in front of that star. And you can't see the Kuiper belt object because it's way too faint and too small for most telescopes on the ground. But when it gets in front of the star, it blocks the light. And then you can't see the star anymore. And your job as an astronomer is to measure when the star disappears and when it reappears. And you know how fast the object is moving on the sky, because we know these things about asteroids and Kuiper belt objects. And if you know how much time it takes to go from disappearing to reappearing, you now measure the size. And if you get enough people out, everybody will see something a little bit different. You can actually map out the shape of the object. And I'll show you an example of that in a little bit. But this tells you not only what the size is and the shape, which is important for planning the observations, but it also tells you where it is at that time. And one single occultation is 100 times more accurate than a single measurement with the Hubble Space Telescope. Very valuable. Okay, we didn't know if we were going to succeed on this, but we were going to give it a try because it was so crucial to the success of the mission, and then we just gave it a shot. Okay, so the timeline gets kind of compressed, and there's more and more and more stuff coming up because we have Encounter coming up on January 1st. We had a Leica campaign, which means we're taking lots and lots of pictures with Hubble in July 2017 to see how fast it's rotating the object, because we kind of wanted to know that. But it also gave us lots of position too. Then we did another occultation on July 10 with the Sophia aircraft. Then another occultation on July 17, which was successful. And then we had another fourth occultation attempt in Senegal on August 4th. And I'll show you some of the details about that. Just 12 days later, we get our first image of MU-69, our target, with New Horizons after our last occultation. So it's a very, very compressed time scale. And now we're starting to do our final navigation in. We do 3 trajectory correction maneuvers to fine-tune our arrival at the target. Now, that's just not because we're bad at aiming the spacecraft. We're very good at that. It's just I'm processing all this data and saying a better and better estimate of where the object actually is and folding that in and correcting the trajectory to match what our best knowledge is. And then we have the insight. So let me kind of dig into a couple of things. I'm actually going to skip a lot of things as I go through here. There's way too much to cover here in the time I have to give to explain this. But back to why wasn't there anything known that we could go to. This is a picture, which isn't the best picture to show. It looks a little crazy, but you've been out in the summertime looking up at the sky in Sagittarius, you know that there's the Milky Way. that bright band of stars with the brightest bits in and around Sagittarius. This is the area of sky that we're looking at here. The most crowded and brightest, naturally brightest part of the sky because of all the stars along that line of sight. This is where we had to look for things that we know could be out there based on what we know about other Kuiper belt objects. We know what typical orbits are. So in 2004, you see this circle here. This is the region of sky that an object would be if it had a typical orbit, that it would, in traveling over between then, 2004 and 2019, where the object would be that New Horizons could get to with the available fuel. And back then, this is a big region of sky. It was very hard. So we did that in 2004 and searching, and just in case there's something really bright, as you see out there, it's very far by. Sadly, there wasn't anything like that. And with each passing year, the search area moves and gets smaller. And you'll notice that the smallest area is in 2014, the year before the Pluto encounter. And that's the year that we finally got back on Hubble. But we were searching very, very hard in these years, and that was, even though we had kind of worked out all our techniques, it just wasn't working good enough. So you might say, well, how bad is it really? So here's an example. It's a tiny, tiny little piece of images that we would take to search for Kuiper belt objects. And if you look up here, there's actually 3 images. So there's one piece here, okay, and then another piece here. These 2 images are of the same patch of sky. Maybe you don't believe me, but if you look very carefully, you'll notice, like, here's 3 stars. You look up here, it's the same 3 stars. It's a little bit different because the atmosphere is not in the same condition. It was a little fuzzier for this picture than it was for that. That's a common problem with ground-based observing, where the atmosphere really kind of messes things up. And it's hard to see what you're looking for here. So using new techniques, which basically allows you to match the images and subtract one from another, you end up with an image like I show on the bottom here, where most of the stars are kind of removed. And then, lo and behold, here's a white dot and a black dot that represents an asteroid. This is an asteroid that's in the main belt of asteroids between Mars and Jupiter. And we know that because of how far it moved during the time. We know it's not a Kuiper belt object. But this object here is probably about 10,000 times brighter than the thing we're looking at. Okay, so, and this is actually even hard to spot. And we're trying to go even fainter. But the ground didn't work. And so then we went on to Hubble. And if you remember that oval in 2014, that's this same oval here. And each one of these squares up here represents the field of view of the camera, the region of the sky that you can get with one picture of Hubble. And it was, I think it was 83 of those boxes that we were going to cover and search with Hubble. And we expected to find 5 objects, and we were hoping that maybe we would have 1 or 2 to choose from. Now, this was a crazy timeline again. We got approved from the TAC on June 13. This is all 2014. Prior to that time, we didn't even know if we were going to get data. And we didn't have data, so we couldn't build our software. And so June 16th, or 13th, we got approval. Got an email message at the end of the day on Friday. Monday morning, I walk in the office. There's images from Hubble waiting to be analyzed. And now I start building the tools to process the data. But it's even more stressful than that, because I knew we only had 2 weeks to process everything and get the answer, because if we didn't find 2 objects in that first 2 weeks of data, they wouldn't let us do the rest of the search. All right, so it's on. We got to really dig in and do this. I was one of 5 teams that were simultaneously and independently processing the same data set. And all of us were writing software, and all of us were trying to process our own data independently. I went through a couple of different versions of the pipeline, and we were putting in fake objects to test the software, and the test was showing me that my stuff was not working. I couldn't find the fake objects. And I went back and made some improvements to the technique, and then I ultimately found a bug in my software. I actually had a sign there. The velocity was backwards. I had a minus sign where there should have been a plus sign, and instead of coherently adding objects, I was not, and it was hiding what I was looking for. And I found that, turned it around, and I fixed it June 26th. So that's just 10 days from when we started getting data to when I had working software, okay? And on Friday, I found the first object. And I was the first one to find anything in the data. Everybody else is, we're having daily meetings and people saying, no, I'm still working on this piece of my pipeline and software. And I don't really have anything yet. And I was doing the same thing until Friday, and they walked into my office for a daily meeting. I just had a number written up on my whiteboard in the back, and I didn't tell anybody what it was. People were walking in and they were looking, what's that? Because they kind of knew my numbering scheme and what I was talking about, and they were wondering, why is there 1110113Y written on the board with a little black border? That was my candidate that I was going to show them at that meeting, and that turns out to be the first object that we discovered. And I said that day in that meeting, you watch, this is the object we're going to fly. And Alan Stern said, who's the principal investigator, the leader of the missions, no, that's not how it works. And I said, well, that's how I would write the Hollywood script. So that's my prediction. So we had a party that night because we finally after all this time, 14 years of work on my part, to find an object. We had one. We didn't know if we could get to it, but I was sure. Then we had a party. Next morning, I'm back at my desk and looking at the data, and I find the second object. So now we fulfilled the conditions of the pilot program. Sunday, I'd finished processing all the data. We had a meeting with Space Telescope, and they approved us for the full search, and it's June 30th. So there we are, 14 days from there. And then we resumed the survey. We found 3 more objects. By July 31st, we found the 5th and last object from the survey. Finished everything, processing was complete August 7th, but we were already recovering objects that we had found. And very quickly we realized PT1s, we made up lots of names for these things. The first was 1110123Y, and then it became PT1, and then it became 2014 U69, and then later got a number, which is 486958, and then we've got a nickname that we created called Ultima Thule. That was the first object, and that's the one we ended up going to. So take that, Alan. Okay, so for this search, I think most of you can understand it. It's kind of a cool little technique how this whole search process works. Because you might think, well, you're just looking at an image, and like Clyde Tombaugh did, you're just looking for something that's moving. It's that easy, right? Well, it isn't. So one field, to search one field with the Space Telescope, we take 2 orbits of time. That's the unit of measure we talk about. Because for each orbit around the Earth, you get about 45 minutes to look at your spot in the sky. If the Earth gets in the way, and you're in the next orbit, and you look again. So the ideal thing is to look in the same spot in 2 consecutive orbits, and you're looking for something that moves. Okay? Everything that we're looking for is moving. There's a variation in velocity that it could be moving, and we know what that variation is. So we take 5 images in one orbit, 5 images in the second orbit, and if we know the velocity, then we could stack all those images up, calculating what that motion is, and it will always be in the same place after we do that calculation. And we stack it up. And we try them all, and we look for where we get a coherent addition of the object on the image. Okay. So here's what an image looks like. This is 1/2 of one image of the 10 that we would take out of all 83 fields. And it's kind of a mess. Did you see these big blotchy things? Those are stars. And this one's probably a star and so forth. But there's a lot of things in there that aren't stars. And if you are really sharp-eyed, you'll see, you might be able to figure out where M69 is in this picture. Anybody see it? Because I kind of cheated. Because it's, yeah? The upper right? Where the green box is? Yeah, it's kind of hard to see. Isn't it? Yeah, the lights are kind of bright.
Okay.
Dim them down a little bit. But there's a tiny little green box to the lower right of that star. Very, very hard to see. I'll show you a better picture here in a second. This doesn't show you all the pixels. So if I zoom in, this is now zooming in so you can see all the pixels. So you can see there's lots of other noise in here. And then with computer processing, what I can do is get rid of the stars, which makes it easier, but it's not easy. And then this is the discovery image of M69. And like I said, I take the velocity, stack them up. If the object is in the same place, then I end up with if I add the 5 images, then I'll have a peak in the image. That's what you see here. And it's in the center of a red circle because I measured it and that's what it is. And then I say in the second image, because I know the velocity that it took to find it and add it up, this tells me where it must be in the second image. And I say the red circle is drawn where it must be, not where it is. And if I have an object that's sitting in the red circle, bingo, I've got an object. Now, the reality is I had to look at 10,000 images that were of nothing but noise to find one image here. And we boiled it all down. And so that was a very happy day when we got this, because we knew we had an extended mission for New Horizons. Now, I'm going to skip a lot of stuff here, but going forward, we have applications. We went to South America and Africa, flew over the Pacific Ocean with a telescope and an airplane, and had to deal with things like wind and big truck to block the wind. It was really cold there in Argentina. Here in South Africa, it was a little bit more comfortable. But these are the telescopes that we dragged down there. And we had about 25 telescopes that we took here. 50 astronomers traveling from the US and Europe, and then locals helping out. And the first one, June 3rd, we deployed everybody out. I did my best. We didn't see anything. For Sophia, the airborne observatory, we can fly wherever we need to, and at the time, we thought we didn't see anything. Turns out we did, but it took us a month or so before we really believed it. This was really cool, flying on an airplane and getting this kind of data. You have a question? What's your question? How old? Oh, you do? That's right. In fact, they're not really flying those too much anymore. But that was really a fun flight. I've never done anything like that before. You know where I sat on takeoff? And the plane took off from the ground? I was right behind that window. I got to sit up there with the pilot. That was so cool. If you ever get a chance to do that, say that. But here's this is what the light curve looks like. So the star's there, and then boom, one little dip down, and then back up. And this is, we just barely clipped the edge of the object here. But and it's taken us a while to figure this out, actually. We're kind of just doing it. But as far as I knew after those two events, we didn't have anything. And we got to the third one, and I said, I'm not going to mess around with this. I'm going to get it this time. Of course, the weather could always screw you up. This is now the southern tip of Argentina. We were working out of a town called Commodore Rivadavia. And every one of these dots here represents where when I put one of the telescopes, and it's a cut across the object where it could be. And then when you put all the data together, here's the and what you see is here, nothing happened, and so forth down here, and then all of a sudden, bingo. Here's a dropout, there's another dropout. 5 adjacent sites together shows that the light disappeared. And if I put that back, do the math, and put it all up on the sky, correcting for everything, I end up with a picture that looks like this. And each these yellow dots represent where the star disappeared and then reappeared. And you can just connect the dots and see that, oh, that's a really weird looking object. When I saw that, I thought immediately, this is what we call a contact binary, 2 objects that are nearly spherical, kind of smushed together. And that's what I told the science team and everybody that we were working with, and they said, well, not so fast. It could also be 2 objects that just happen to be overlapping. Or it could look like what I was talking about. Or it could just be some crazy shape object. We said, okay, fine. Let's get some more data. So we go out to do the 2018. We want to get another measurement, and we want to get another size. If it's a contact binary, we're going to see only 1 hit from the object. If it's a close binary, you should see 2 the other time. The odds of getting an overlap on both of them is 0. So I sent most of my teams to Senegal, and then a few teams to Colombia. And the weather was not good at either location, but good enough. And we were working with the international teams, both the Colombians and Mexicans worked together with our teams in Colombia, and we also had French astronomers and the Senegalese, and NASA headquarters representative here, Adriana Campo. It was an amazing thing. And as I mentioned before, I got to meet President Sall in Senegal. In the middle of our stay there, we got a call from his office saying he wanted to meet us. And I thought he meant me and maybe my deputy or something like that. But he really meant he wanted to meet the entire observing team, all of the Senegalese and everything. Okay, I guess we're not practicing today. But we went and had this nice conference. This is actually the ambassador, the U.S. ambassador to Senegal. I'm afraid I still can't remember his name. It's very complicated. He's originally from Congo, but is a U.S. citizen now. Funny guy. But I've never been trained to do this kind of stuff. But, occultations takes you weird places. So. And this is not spectators. This is the team. Lots and lots of people here, Senegalese and U.S. and French astronomers, all working together to get this data. And there's the family portrait of everybody. It was quite an experience. So it was cloudy in Colombia, unfortunately. It was mostly cloudy in Senegal, but we got a couple of dips. Here's our best one. Just less than a second dropout for the object, but representing 19 kilometers across. And then just to the south, here's another one. Those are our 2 chords. We got it. We got a new position. I'm still trying to figure out exactly what this is telling us. I'll have that answer probably in another week or 2. But it gave us reassurance that the measurements we were getting from Hubble and from the occultations were good, and we were ready to go for the occultation. Okay, so let me move ahead, and I want to show you some of the things from New Horizons. Can you see MU69 in this? These are pictures taken by this New Horizons spacecraft. You might want to dim the lights a bit. See it? So it's just you're approaching it, so it's getting brighter, and it's moving a little bit, because you're going straight at it. Okay. Then when I take away the stars, that's what you see. And this is about all we had until about a week before encounter. But it was still very exciting. And this data gave us confidence that we were actually going in the right place. So on New Year's Eve, this is the picture we got. Not very exciting, really. It was just a smudgy blob. But you'll notice it kind of looks like two circles stuck together, right? So I was pretty excited because that meant, I more or less knew from the occultation stuff that we had a contact binary, and this was my first indication that was actually right. But the next day, I like this picture. This is kind of cool. This drunken snowman kind of thing, which here it's upside down now, but it spins around in space. So here we're getting to know this new object in the outer solar system, and almost immediately everybody's looking at this and saying, wow, this is not like anything we've ever seen before. This really is an object that has not been processed and modified. If you look at our moon, you see all sorts of stuff going on in the moon, including craters, which means that it's been bashed up and mushed around and changed over the age of the solar system. And the same is true for the asteroids, clearly for the Earth, with all the weather and plate tectonics and things going on there. Going out to this part of the solar system where nothing happens, this thing has been in the deep freeze for 4.5 billion years. And for us looking at this, we're actually seeing it. So I have to go back and show how good we did with the occultations. This is an overlay showing all the occultation parts. Actually, we'll just bring that again so they can see. So you can see the outline from the New Horizons imagery, and then the circles fitted to where the occultations said the outline of the object is. Now you notice it's not perfect, but this is topography. You have to have high resolution pictures to figure this out. I can call this a total win. And in fact, it helps give us a view of the object from a different vantage point, and ultimately we get a better measurement of the shape of the object by putting all this stuff together. So here's kind of one of the approach movies showing it. We're getting closer, so what's happening is we've scaled it so it's the same size. So those are the individual pictures, and that's a little movie. But it's getting sharper and sharper and sharper as we go. And let's go ahead and go to one of the cool new images. This is what we got just before close approach. And wow, we had some of the most fun discussions I've ever had as a working scientist in my career, talking about what do we see here. And then I'll just go ahead and go to the best pictures that we got so far. I think these just came out in press releases last week. So hot off the press. You can see things that look like craters over here. There are these white lines and all sorts of stuff. And all of a sudden now, the planetary scientist in all of us starts to come out trying to figure out what are we looking at here. So I'll tell you very briefly what I see. And that is, I think these little bright lines here represent edges between units. Imagine taking, this is taking something that's a few miles across, a big fluff ball of stuff, not very dense, but water, ice, and rock, fluff ball, that are all about, say, yay big. And you can kind of, if you look at the original images, it's a little fuzzy up here, but you can draw boundaries that makes it look like it's sort of built up like 8 of these fluff balls here around the middle fluff ball, and this might be like 4 of them stuck together. So at some point, maybe these things were all swarmed around each other and they finally coalesced and turned into a larger object. And then there were two of them, and there was probably a third that was thrown away. And then these two came and joined together, and you can see it kind of looks a little bit asymmetric. Like maybe they touched and it shredded it just a little bit and distorted the neck, because it's like smoother here and steeper here. And then maybe kind of rotated a little bit. And then once those came together, basically nothing else happened until New Horizons flew by. And we're going to be working on this for a long period of time, I'm sure. We've got a lot of new stuff that's coming out. We're talking about it at the Lunar and Planetary Science Conference in Houston in just a few weeks. And there'll be more press releases coming out. New Horizons is still beaming data back to us. It's going to take about a year and a half to play back all the images and get it to the ground so we get it on our computers. These results will continue to improve. And we are continuing to fly out into the outer solar system. We're going to make distant observations of other Kuiper belt objects. And we're going to be busy with that for a couple of years. And then after that, we still have a healthy spacecraft. The way I like to think about it is that we have an observatory that happens to be out in the Kuiper belt. There's an 8-inch telescope on board, and we're going to look for interesting and innovative things to do with that facility for decades to come. We don't know exactly how long it's going to last. It could be, we think it's pretty certain that it's going to last 20, maybe 30 years. It's more driven by the power budget on board the spacecraft before we run out of power enough to transmit data back to the Earth. But we've got a long way to go, and there's some really interesting things we can do with the spacecraft going forward. But this has been an incredible journey, and I worked with so many people to get to this point. There's one final point that I want to make, and then I can take some questions if you're curious. If we had not done any of the occultations, you would never have seen these pictures, because we just didn't know accurately enough where the object was going to be in order to aim New Horizons to be in the right place, and also to aim its cameras to point in the right direction. If the likelihood of getting these pictures was maybe, we had a 1% chance of success, if that. With the first occultation in July 17, that brought the odds up to, I don't know, something like 10 or 20% that we would get something. But the odds of getting all of this object were essentially not nil. But with the two occultations and everything else that we did and putting it all together, we got this picture, and the gap between the edge of ME69 and the bottom of the image was about 250 meters. And if it had been 250 meters off more in the bottom, it would start to pivot. So we won the lottery, I don't know, maybe 100 times over throughout this entire project. But it was very gratifying for, basically 2 years of intense work on my part on the applications and the navigation, helping out with the team, that this image was a success, and we got all of the other. So we got what we came for. So with that, I will close and take questions. Thank you very much. Okay.
How big is the object?
It's, the long axis is roughly 30 kilometers. So it's not very big. If you remember the pictures, I didn't have, we've got so much stuff I could show, but if you remember pictures of Pluto, one of our team members put a copy of ME69 to scale, sitting as if it's sitting in the middle of the big nitrogen ice lake on Pluto, and it's about the size of one of the mountains on Pluto. Yeah.
Isn't the bigger piece roughly the same size as the valley? For Las Vegas Valley? It's about The bigger piece is like 17 kilometers across or so.
Yeah. And they,
Oh, wow.
So it's about, the big piece would actually fit down into the valley of Las Vegas very nicely. So.
Wouldn't be pleasant.
Yeah, we're working on some other comparisons. I'm working with this artist. We're trying to compare it to other things in pop culture. And I think I figured out that Babylon 5, some of you like that TV show?
Yeah.
The space station.
Mm-hmm.
The length of Babylon 5 is about this long.
Oh, wow.
And the Borg ship from Star Trek turns out to be about this big. That's pretty big, right?
Yeah.
And I think the Death Star from Star Wars, the first one was maybe about half the size of this guy.
Oh, wow.
Yep.
It kind of looks like an atomic BB-8.
Yeah, we've heard that a lot. Yeah. But it's not, when you look at this, you think that there's two spheres, like BB-8. But it's not two spheres. And it's the shape of this piece here is a bit more like a hamburger pan. It's kind of squished in one direction. And this one's squished too, but not as much. And so it's actually not really a contact binary in terms of two spheres stuck together. It's a little bit more complicated than that. But that's actually even cooler because the theory, the guys that do the theory and try to figure out what this all means and how to put it together, they don't know what's going on. Which is great because that means there's more to learn. Once we kind of figure that out, we'll understand more about how the solar system forms. And just one perspective from my own part, Pluto is always going to be my favorite. I split so much time and effort of my life in understanding it, and the pictures that we got back with New Horizons were just absolutely spectacular. But in terms of fundamental contributions to understanding where it came from, how the solar system forms, this one rules. It's going to tell us more than all these other things.
Do we know anything about the composition of the object?
We're still working on that. The data that we're able to take is limited. We don't have any direct compositional information. We can tell you what it's not, and that is it's not covered in water ice. Okay? It's covered in some reddish material, which we know is very common in our solar system, and we think we have some ideas on that, but we're still working on it. And Pluto's got lots of red stuff on it too, and the big question is the red stuff that's on this guy the same as the red stuff that's on Pluto? And maybe it is, maybe it isn't. We're still working on it. But the other part of this is the density of the object. If you know what the bulk density of the material is, it tells you something about the composition. And there's reason to believe that this is a very, very low density construct. About a third of the density of water, which is extremely low. Now, that's not a solid measurement, but that's an indication of there's a story you can build around that makes sense.
So could it be hollow? Could it be hollow?
Well, hollow in the sense that it's got porosity. So if you take ice and let it freeze very slowly, and it's very dense and compact, there's no air in it, low porosity, it has a density of 1. You take that ice cube and shred it into a bunch of snowflakes, and now it's 10 times bigger, its density is going to be 0.9. Okay? This is what's going on here, is in the early accretion, I think we're seeing that you've got these fluff balls, that's what I call them, that there's a lot of gaps in between the material there because there's not enough gravity to squish it down, they're not smashing into each other, they just kind of settle like snowflakes do. You recently seen snow right here. That as it settles out, when snow first falls, it's very, very puffy most of the time. This is really wet stuff. And then over time, it compacts. And we think that's part of what's going on. But we infer that there's got to be a lot of ice in there, but we just don't know in detail. Any question?
You mentioned that it was going to take about a year and a half to get all the imagery. I just wondering what kind of download bandwidth you get from all the way out in that part.
Okay, so you'll probably recognize the answer in the description. Remember modems?
Yes.
Way back when.
300 balls.
Well, yeah, it's when it's doing nothing but sending data, it's equivalent to a 1200 baud number.
Oh wow, 1200 bits per second.
Yeah, and we have to transmit, what is it, like 40 gigabits of data back?
That's it.
And so we're spending a lot of shifts every day, 8 hours on the biggest radio telescopes that NASA owns to beam that data back.
Deep space network.
Exactly. Now, we do kind of know what's in the data, so we've prioritized it, so it's not just throwing it together. We're sending the juicy bits back. And so, maybe we'll think we've got everything to give up sending blank pictures back towards the end, but it's going to be a while.
Yeah.
You got a question? No?
How is the travel from the spacecraft to the receivers?
One-way transmission time is about 6 hours. So if you want to talk to the spacecraft, you say, "How are you?" 6 hours later, the spacecraft gets it, and it says, "I'm fine." 6 hours later, it's you hear the answer. So it's a 12-hour round trip. And it's a cool thing that's going on right now that will last for a certain period of time, that the same receiver that sent the query can see the answer. Usually it's a different receiver. Yeah, the solar system is a big place.
You mentioned earlier that the Kuiper belt is considered kind of like the third region of the solar system, and the Oort cloud is considered the fourth. Or something.
Well, I think when the day comes that we can directly investigate the Oort cloud, whoever it is that's building that mission will probably say, "Okay, we're doing the fourth one." But right now, it's just considered to be an extension of the Kuiper, simply because it's so hard to get anything out.
There's no data to differentiate them.
Yeah, I mean, we have a little bit, but I could see if this was your thing and you were doing the PR thing for Oort cloud mission, we'd be calling it the fourth sign. Nobody's really doing it. The thing is that material that's in the Oort cloud is probably not as primitive, meaning unaltered, as what we're looking at here. This is probably the most undisturbed material in all of the solar system.
Is that because of interactions with other solar systems that we pass by?
Well, and within our own solar system, because comets we think were formed closer to the sun and then hurled out into the Oort cloud, and then they come back. So they've been processed and manipulated over time. These guys were born there and lived there all their lives, at that distance from the sun, and haven't changed. That's the whole idea, and everything that we're seeing here says that that's the right answer. That's really what's going on. These are the best fossil beds in all of the solar system.
Truly a primordial object.
Yes, that's what we were searching for, and to get these pictures and finally look at them and realize we got it. That was very exciting.
Is the orbit more or less circular than this object?
Around the sun, right?
Yeah, around the sun.
Yes, it's very close to circular. And it's also very close to being in the plane of the solar system, too. And that's one of the key things. It's not just that object being in that orbit, it's that it has lots of buddies that have exactly the same orbit. And then we see lots of other Kuiper belt objects that aren't. They're inclined and eccentric orbits. Those are the ones that have been disturbed. And we can tell the difference between the ones that have been kicked around and the ones that haven't.
So I think I read something about a potential line the same time that people look at how far the line is. What's the status of that?
Well, this is one theory that's out there. It's very exciting to find planets. Percival Lowell was caught up in that, and that's what led to finding Pluto. He was part of the Planet Prediction of the Month Club. He and Pickering were doing it out, and every month they said, no, it's over here, no, it's over here. And there was no data to base that on, as it turns out. So it's just, well, let's look everywhere. And that lure is still around today. We've got bigger telescopes and better instruments, and you can look further out. So let's look for something like that. And in fact, if you're looking for something really slow, let's say it's 10 times farther out from the sun than where this guy is, the only things you're going to be able to see are big things. And there are people out there looking at them. Now, the other part of this is that you can say, well, there's big things on the elliptical orbit, it comes back in, zooms around, it's going to leave behind a signature of objects that don't exist, of orbits that don't exist, because it's been ruled out because that bigger object is trying to screw things up. That's been the logic that's been out there to guide where people are searching. And my own personal opinion on that is that they're just seeing observational bias. They're seeing things just because we don't have enough data. And you haven't been able to take out those biases. And you see certain things, but it's only because that's what you can see, not because that's what's there. I think this will all, in another 10 years, is all going to go away. We're going to know what's out there. And if there's another, I prefer to call it Planet X, just to be a little bit more PC. I think people that are using Planet now are getting inflammatory. They're trying to depress. They're trying to say, oh yeah, we got rid of that shark there, Pluto. We're back on the real planet. We don't need to do that. Discovery is great. Let's find stuff that's out there. Let's make it about what we discover, not what we call it. But Planet X is just another big planet. I think it's really very exciting to find it. I'm not so sure that there's anything that's close in. I've looked a lot at these objects, and I think I'm seeing that there are big things, like there's an Earth-sized object out there. It's way big out there. We just don't have what it takes to find it. But I think we're learning enough about how the solar system forms, including objects like this, that's going to constrain the likelihood of it being something big. So it's all connected.
This has a more planetary style orbit instead of like an orbit like a comet. Some people think it's really restricted. It's really surprising.
Well, think about what happens to a comet. How long does a comet live?
It's 2 years, sometimes one pass.
Exactly.
Gets kicked out of the solar system.
So that means it hasn't lived for 4 billion years in an orbit that takes you by the sun, right?
Right.
So that means it used to be somewhere else. You don't know where that somewhere else is. Okay? Now, what we do know is this object has been there all this time, so there's been nothing to affect it. So that means that we have never seen a comet made out of something that started here and went directly in to the solar system. Now, it's possible, that you can still lose objects out of that region, but it's a very long pathway. And so what happens? Maybe an object here has a chance encounter with another one of its buddies, and the two of them get, they get pushed out a little bit, and that gets them close enough. But Neptune starts tugging on it, and it meets up with another one, and all of a sudden it's a more excited, classical or non-classical, but excited orbit object. And then it runs into Uranus, and then gets going into the solar system, and then it gets shredded, and stuff happens to comets before we get to see them. And so we've always called comets primitive objects, and they're more primitive than asteroids. But this is the real deal. It's a lot to chew on, huh?
Yeah, it really is.
Yeah, that's the way I feel too. Sometimes I just sit there and just stare at this thing. Wow.
The material from the accretion disk around the sun that formed the planets, it's like, it really is that ring that far out, just solidified into that object, and probably hasn't been disturbed since then.
Right. So, big question: are all cold classical objects that have that kind of orbit at this size, do they all look like this, or is this one weird? Now, Occam's razor, or finding the simplest explanation, says this is common. But this is a testable hypothesis. And how do we test that? We could launch a bunch of spacecraft and fly around and look at all these things and figure it out. It'd be kind of expensive. But I've got this other technique called occultations, that I can explore this region of space here and now with smaller telescopes that I send around. And I'm scrambling like crazy because now everybody in the science community realizes what occultations can do for us. And try to find a way to capture that opportunity and learn more about these things and find out if this is weird or not.
And two members of the Las Vegas Astronomical Society.
Yeah.
Bob, that's what professor from here, Brian was.
Yep. Yeah, in fact, just before Recon started, this is a big project I've got. I didn't really talk about here in this talk, but we've got telescopes all up and down the western United States looking at occultations of Kuiper belt objects. There was a key meeting of the International Occultation Timing Association North American chapter that was held right here on this campus, in the next building over, that I came here to talk to them to get their ideas on how to build a network like Recon. And that was a while ago, but so I've been through here before. I actually used to work at Lowell Observatory, so this is my backyard, so to speak.
Probably talked to Paul Mayer.
Oh yeah. Paul's actually done some observing for me, been part of one of my occultation campaigns, and got to know him during those kind of meetings. Our paths cross fairly often.
Paul to come here, asked us to organize volunteers for him to go out and do mean belt asteroid occultation observing stations. Jerry, myself, and a number of other members who have done that before.
Yeah, we had an occultation of Tropos back in, when was that, 2010? That some of you may have actually deployed some of Paul's cameras.
Probably Rob Lambert, our former president.
There were several stations in this area
Yeah.
that contributed that. We got a really nice pickup. And that's one of the targets for the Lucy mission, is that particular object. We were doing the application.
So that's a Trojan asteroid.
Jupiter Trojan.
And just to wrap up, I just wanted to thank you for telling and walking this group. I know you have to get on the road,
Yep.
but we'll read around as long as you'd like to. But during safe tonight, going back to Colorado, we can get there by tomorrow.
Yeah, it's quite the treadmill.
Yeah.
I've just got 2 weeks left to get ready for the Lunar Planetary Science Conference. I'm trying to get my final results before we go. I'll know a lot more about this guy by the time I do my talk in Houston. And got all sorts of things going on in free time, busy time, but it's fun.
Okay, yeah, we just had this, they just had a 3-day conference that we came
Well, thanks for having me.
Thanks.